Hey everyone, really excited to be here. My name's Anupra, I'm 16, and today I'm going to be talking about a project that I've been working on in the IoT space to better detect disease and better understand or demystify our brains. But before we get into all the fun tech stuff, I thought I'd start with how I was super excited to find out that I'd be talking about IoT today. Specifically because I think it's super interesting how nowadays we have so many different devices, from our phones to sensors to smart thermostats, that can help us gather insights and improve processes in our outer world. What I've been asking myself is, what about our inner world? Organs like our brain, some of our most complex and mysterious, yet also some of our most important. That's the question that led me to a lot of the interesting experiences I've had in the neurobiology space. For example, just this summer, I worked with a really cool company called Apollo Neuroscience, who's creating the first wearables to help to combat chronic stress. I have also worked with labs at the UHN, one of the largest health networks in Canada, to identify proteins, which are basically the building blocks for all the reactions that happen in your brain, that could indicate Parkinson's disease. But one of my biggest aha moments from working on all these different projects actually came from shadowing at a clinic where they tried to treat neurological diseases like Alzheimer's and Parkinson's. Because this is where I realized that even with all this super exciting research that I was doing in the space of neurobiology, very little of it was actually reaching our healthcare systems. And therefore, very little was reaching the people who need these advancements most, the people affected by neurological disorders, which, by the way, is 1/6 of the entire world population. But even if we zoom in on a very specific disease, like Alzheimer's, one of the main ones treated at that clinic, that affects around 50 million people, though that number could triple by the year 2050 thanks to the aging population, which is a really significant number. But what completely boggled my mind is that only 25% of Alzheimer's cases are detected early enough to make a proper therapeutic intervention or to treat the disease with any good chance of improving quality of life. And while I was at this clinic, I got to see firsthand why this was the case, why that number was so low. I saw patient after patient go through our current Alzheimer's diagnosis process, where, first of all, they would have had to show symptoms for Alzheimer's disease, like memory loss, before even having a chance of getting diagnosed. Once they were there, I would see the doctor ask them a few questions about their cognition and perform a few tasks so they could see a physical exam. And then, based on that, if the doctor maybe suspected that they might have had Alzheimer's, they'd get an MRI scan to see the structure of their brain, or other types of imaging scans, or a blood test to rule out any other diseases by seeing any compounds in the blood, and sometimes a genetic test. Though that doesn't really tell you what's going on in your brain, that more tells you your risk of diseases like Alzheimer's based on your genes. The whole issue with this that I saw was that, based on all this research that I was doing in labs, the root cause of Alzheimer's disease was not all of these symptoms. It was specific changes to the proteins in your brain chemistry. And these changes can happen 10 to 20 years before you even start to show symptoms. By that logic, that means I could have a disease forming in my brain right now, and I just wouldn't know until I start to show symptoms, which could be years down the line. How can we expect to catch disease on time with the current methods we have if we don't even know what we're looking for? This experience shadowing at a clinic allowed me to ask myself, okay, our existing system is not optimal, but what do I think healthcare should look like in the future then? I realized that there needed to be a way to continuously monitor our brain for disease rather than just waiting for symptoms to arise. Kind of like the way a Fitbit can continuously monitor your heart rate, but instead of that, some sort of device that could continuously monitor the way your proteins in your brain are currently working and whether any changes to your proteins might indicate disease. So I've been looking into how we can actually do this using the Internet of Things. This is where IoT actually comes in, making our bodies more connected. But instead of just any Internet of Things device, I'm specifically focusing on the Internet of Nano Things, or nanosensors. Nanotechnology is really interesting because it involves materials hundreds of thousands of times smaller than the width of a human hair on the nanoscale. And because these materials are so small, literally the size of atoms or molecules, they have really interesting properties that we don't even necessarily see on the larger macro scale, which have some really interesting applications. I almost like to think of them as kind of magic because we don't always know why these properties exist. But like I said, they can be used in many different ways. I'm specifically looking into how we can use nanotech, or specifically nanosensors made with carbon nanotubes, to detect amyloid plaques, which are a specific type of protein that's often misfolded when Alzheimer's exists. So this is specifically for the Alzheimer's application. And although there are many other markers that could be used for Alzheimer's disease, I'm focusing specifically on the amyloid one. So although the sensor is made up of a lot more components than just carbon nanotubes, the carbon nanotube is probably the most important part of it. It's basically exactly what it sounds like, a tube made of carbon atoms. But it's really interesting because it has the unique magical property of being really sensitive to electrical changes. So it can basically harness the action of coming into contact with an amyloid plaque and take that, harness it as a positive voltage or an electrical signal. So that would basically be an indication that, oh, there's this marker of disease in our brain right now. And it can send that information to an external device in the future through nano antenna, which can also be made of carbon nanotubes. These would be transmitted at a frequency low enough, around terahertz, that would make sure that it wouldn't harm any neighboring cells. Now, the sensor's ability to actually come into contact with the amyloid plaque happens through the aptamer, which is this biological molecule. Its main purpose, like I said, is just to bind to the amyloid plaque and tell the carbon nanotube, okay, this contact is happening. And the aptamer that I would use has already been engineered in labs to specifically bind only to the amyloid plaque. And you wouldn't even have to cut open your brain in order to get this sensor in there. This could be injected intravenously and then cross the blood-brain barrier all by itself. The blood-brain barrier is basically exactly what it sounds like, the barrier between your blood vessels and your brain, which is technically a closed-loop system. And it's able to do this by basically attaching itself to amines, which are molecules that can naturally cross the blood-brain barrier through transfer proteins, kind of like a chauffeur. What the sensor does once it's attached to amines is basically trick the blood-brain barrier and the transfer proteins into thinking it's an amine when really it's not. So kind of like buying a fake ticket to get with the chauffeur and drive to another location. But instead of committing fraud, you're helping to detect disease, which is a lot better. Now, I'm currently at the stage where this sensor, it's currently in proposal stages. So I've written out how this could actually work, and I'm trying to get with labs to figure out how I can improve it and how I could possibly run experiments on mice models. But once this specific application with Alzheimer's disease, once we figure out if this could actually work and try to validate that it works in mouse models, the possibilities could really extend way further. As long as you have an aptamer that can bind to whatever protein or biological molecule you want it to, it can detect pretty much any disease. And if you can have nanomaterials that can perform other functions, like delivering drugs to a diseased part of the brain, these could communicate with each other on the nanoscale, therefore increasing the connectivity in your body. So if disease is detected, treatment can be delivered right away in a closed-loop system. Or even better, what if this sensor could communicate with external devices, like sending a message to your doctor if it indicates any disease? It's really exciting to see where this could go. And although there's a lot of things that I would have to work out, like how to make sure the sensor doesn't become toxic to the brain with the materials used, or even how to make sure we can remove the sensor safely, and once this actually does get implemented into humans, how to make sure the data that's collected only stays with the people who need to have the data, so making sure security exists. Although there are all these different barriers, I'm really excited for a future when we can overcome these, and where everyone could have this sensor to help prevent disease in the brain and detect it earlier. Nowadays, when I shadow at clinics, I like to hear about the experiences of the patients as they go through this diagnosis process, and I like to tell them about all these new innovations in nanotech and nanosensors, and how these could really help improve the experience, so that in the future, when people like me are shadowing at clinics, they can actually see treatment happening rather than just late diagnosis. It's time we start to understand as much about our inner world and our brain as we do our outer world. Thank you so much for listening. If any of you are interested in learning more about what I'm up to, here's some of my contact information.